We looked at basic properties of waves, we looked at superposition and the Doppler effect. Now we're going to look at standing waves, which is actually the result of superposition. So a standing wave is a wave that is trapped and cannot travel in either direction. You created these when we did that lab with the slinky in that third part. So it's a lot easier to see if you have a thin string and a very lot of tension. We don't have one for me to actually demo, but I will show you a video of what the standing waves actually look like. So what happens with standing waves is that individual points on a string are going to oscillate up and down, but the wave itself is not traveling. So the crests and troughs will look like they're standing in place, and this is created by superposition. So what your standing wave will look like is something like this. And you do have a picture right underneath this explaining what these are. So you're going to have nodes and antinodes. The node is the point in a standing wave pattern that never moves. So think of the node as the point on the equilibrium. And these are going to be spaced lambda over 2 apart. So in other words, they are a half wavelength apart. Your antinode is where the crests and the troughs are. So it's halfway between the nodes where the particles in the medium oscillate with maximum displacement. Looking at the picture, it's very self-explanatory. Nodes are where the equilibrium points are, and antinodes are halfway between the nodes, so that's going to be your maximum displacement from the equilibrium. Nodes and antinodes are both spaced a half wavelength apart. So because they're spaced a half wavelength apart, the wavelength would be twice the distance between successive nodes or antinodes. Nothing really to memorize other than knowing that this is one wavelength. So from here to here is one wavelength, which is why you've got 2 antinodes. So 2 times 1/2, this would be one wavelength. So a quick example, what is the wavelength of this standing wave? So if you go from 0.5 to 1, that's a distance of 0.5. So 0.5 equals lambda over 2, this is meters, then 1 meter equals lambda. This isn't an equation you'll be given, it's just something that you're gonna need to know. So basics of a standing wave, let's now look at how they're created. In order to have a standing wave, you need to have a boundary. And all a boundary is something that the wave will reflect off of. When you were using the slinkies, the boundary was your hand. A lot of times the boundary will be just a fixed point where the wave hits it and then it's going to reflect backwards. In an ideal situation, all of the energy is reflected, so the amplitude is going to stay the same. However, it's going to be upside down. So the wave travels this way, hits the boundary, and then goes like that. So that's why you see the before and the after. What happens with a standing wave is you're going to have 2 boundaries and they're both reflecting. So in order for a standing wave to occur, you need 2 conditions. First, you need a node at both ends of the string, and second, those nodes need to be equally spaced. So one way to create a standing wave. 1, you need the 2 boundaries, 1 at either end, where there are nodes, and 2, those nodes must be equally spaced. So what actually goes on with this, you're going to have your 2 waves. So you create your disturbance in the middle of the string. The 2 waves are going to move out, they're going to hit the boundary, and then they're going to move back towards each other. And when they're moving back towards each other, I'll draw this in the 2 different colors. So let's say the one wave is traveling that way, while the other wave, let me make this a little bit more. Let me redo this in different colors. So here's the equilibrium, here's the wall. We have one wave doing that, and then we have the second wave doing that. So what we actually have going on, and this is just going back and forth, back and forth, back and forth because of those 2 boundaries where the wave can't go through, you have constructive interference and destructive interference, and constructive and destructive, and it's just happening over and over and over again, and that's where we get our standing wave from. There are three possible, this would actually just say possible modes of a string. It's not only three. And I think your notes is right. Let's get rid of possible. So different modes of a string. All the mode number tells you is how many possible waves there are in a standing wave. It's equal to the number of antinodes on the standing wave. The symbol for mode is an M, so this makes perfect sense. Mode is M. If you have M equals 1, then it's one wave, M equals 2, it's two waves, etc. So this is what M equals 1 looks like. So you have one wave, two waves. I'm sorry, half a wave, the other half a wave, so there's one full wave. Here you've got one wave, another wave, so there's two waves. Here you have 1.5 plus 1.5, so there's three possible waves. So again, mode number comes from the number of antinodes. So if you have one antinode, then there's one possible wave. Two antinodes is two possible waves. Three antinodes is three possible waves. Okay, different modes are going to have different wavelengths, and this is given by the equation. Lambda m equals 2L over m. M equals, oops, that should be equals. M is going to equal 1, 2, 3, etc. So that's just the mode number. Lambda is the wavelength, and L is the length of the string. So for M equals 1, lambda 1 would be just 2 times the length of the string. So that's telling you the length of the wave. And if you remember, the distance between the nodes is 1/2 a wave. So that makes sense, where 2 times the distance between would be the wavelength. Standing waves can exist on the string only if its wavelength is one of the values given by the equation above. Resonant modes are frequencies at which the wave wants to oscillate, and this is also known as a resonance. So if you're seeing a question talking about resonant modes or resonances, it's the same thing, and it refers to frequencies. Remember, frequency and wavelength are inversely related. The fundamental frequency is the first mode of the standing wave modes. So fundamental frequency is for mode 1, so that's where the F1 comes from. That's going to equal the speed over 2L. Think of it this way. We know that speed equals F lambda. We know that lambda for a standing wave is equal to, so this would be 2 times 2L over M. If M equals 1, V over 2L equals the frequency. So that's where this comes from. In terms of the fundamental frequency, so if you have a mode that is not 1, the frequency of whatever that mode is just equal to the number m times the fundamental frequency. And again, that's where m equals 1, 2, 3, etc. Harmonic is just a sequence of possible frequencies. So if you hear like first harmonic, second harmonic, third harmonic, that's referring to this. So F2 would be the second harmonic, F3 would be the third harmonic, and so on. Let me do 2 quick examples. First, it tells us that a 2.5 meter long string vibrates as a 100 hertz standing wave with nodes at 1 meter and 1.5 meters from one end of the string and at no points in between these two. First, which harmonic is this? Second, what is the string's fundamental frequency? And third, what is the speed of the traveling waves on the string? We want to start by drawing the standing wave. So we're going to have the 2 boundaries. Here's the center. It's 2.5 meters long. So this distance right here is 2.5 meters. We know that we have nodes that are 0.5 meters apart. So what I want to do is break this apart. So we know that this is going to be 0. This will be 2.5. We want to break this apart into increments of 0.5. So 1, 2, 3, 4. This would be 0.5 meters, 1 meter, 1.5 meters, and 2 meters. It tells us that there are nodes at 1 meter and 1.5 meter and no points in between these two. All that means is that the nodes are spaced 0.5 meters apart. It does not mean that these are the only two nodes on the standing wave. So if they're spaced 0.5 meters apart, I've got all of these nodes right here, and then I want to draw in the standing wave. So here's the one wave, and here's the other wave. Drawing that wave allows me to answer the first question, which harmonic is this? So remember, the harmonic is the mode number, and that refers to the number of antinodes. So there's 1, 2, 3, 4, 5 antinodes. So that means that this is the fifth harmonic. Or we could just say that m equals 5. Next question is asking for the string's fundamental frequency. So with 5, or m equals 5, so with the 5 antinodes, we know that the frequency for the fifth harmonic equals 100 hertz. We also know that the frequency for the fifth harmonic is going to equal 5 times the fundamental frequency. So the fundamental frequency is just equal to 100 hertz divided by 5, or 20 hertz. The last thing it's asking for is the speed of the traveling waves on the string. So because the string is the same, it's not changing, the tension's not changing, the speed, no matter what harmonic you're in, is going to be the same. So in order to find speed, we know that speed equals f lambda. We have the frequency for the fifth harmonic, we have the frequency for the first harmonic, but we don't have the wavelength. You can find the wavelength for either of them. We know that lambda m equals 2L over m. So if we do it for the first harmonic, this would just be 2 times 2.5 meters over 1. So the wavelength for the first harmonic would be 5 meters. If wavelength is 5 meters, then speed equals 5 meters times the frequency for the first harmonic, or 20 hertz. 5 times 20 equals 100 meters per second. Just to prove that speed is the same no matter what frequency you're dealing with, let's look for the fifth harmonic. So we knew that the fifth harmonic, the frequency was equal to 100 hertz. Lambda for the fifth harmonic would equal 2 times 2.5 meters divided by 5. So lambda would equal 1 meter. Speed equals f lambda. So 100 hertz times 1 meter, or 100 meters per second. So again, just reinforcing that the only thing determining wave speed would be the medium. Since the medium here doesn't change, your frequency and wavelength will, but that speed will stay constant. I'll do one more really quick example. It tells us that a helium neon laser emits light of wavelength 633 nanometers. A typical cavity for such a laser is 15 centimeters long. We want to know the mode number of the standing wave in this cavity. I'm not going to draw this standing wave, and you'll see why in a minute. I'm just going to list what we know. So we're given that the wavelength lambda is 633 nanometers. That's 633 times 10 to the negative 9th meters. We also know that the length where that standing wave is going to be in is 15 centimeters. So that's 0.15 meters. And we're looking for m. Wavelength, oops, I keep making these look like x's. Wavelength for this certain number mode is equal to 2L over m. So m equals 2L over lambda. We have L, we have lambda. So this equals 2 times 0.15 meters divided by 633 times 10 to the negative 9th meters. And this equals 4.73, keeps on going, times 10 to the fifth. This is unitless because those meters cancel out. So your M is about 4.7 times 10 to the fifth. So a huge, huge, huge number for harmonics, but if you think about it, light has very, very, very small wavelengths, so that makes sense. We'll do some practice with this, drawing standing waves with different harmonics and then figuring out either frequency, wavelength, or speed, and then we'll apply this to sound waves.